Hello, my name is Bill Moore, and I'm a Senior Verification Engineer with ParadigmWorks. The title of my presentation is Gherkin Implementation in SystemVerilog Brings Agile Behavior-Driven Development to UVM. Given your project is in a pickle, no matter how you slice it, and your coworkers are getting salty, and you're starting to feel a crunch, when you introduce a cool solution like BDD, then your communication should be crisp, and everyone should say, "You're the real deal." And with that out of the way, let's begin. A couple years ago, I had never heard of Gherkin or behavior-driven development. They may be new to you as well, so I'll start by explaining the problems they're trying to solve. Every silicon project ever relies on documentation to keep teams on the same page. You have requirements documents, design specs, verification plans, status reports, and so on. Documentation is key, and yet there are some common problems that I'm sure you've experienced. First, it's static. You create your document in a word processor or online editor, and it just sits there. You can't execute it or automatically verify it when change requests or bug fixes arise. Next, it's asynchronous, meaning documentation and implementation happen independently. The waterfall model, where documentation blocks implementation, can be overly rigid and inefficient. But just-in-time documentation can be just too late. Next, quite often, documentation lives separately from the design code it's documenting. In pretty much every project I've ever worked on, the documentation is created on a personal computer and distributed through groupware, but the source code is managed by revision control software on a completely different server somewhere. It's awkward to keep the versions in sync. Documentation is often richly formatted with nice fonts and diagrams, which is great, but that makes it hard to use the document in your design or verification. As a DV engineer, I love seeing pretty tables in a design spec, but then I have to retype that whole table so I can use it, or try to copy and paste it. Good luck with that. And now there are two copies of the table, which is an opening for bugs to creep in. Documentation is specialized, so there may be a technical language barrier between the writer and reader if they're from different disciplines, like software and hardware, or design and verification, or digital and analog. Without ubiquitous language, it's easy for meaning to get missed across domains. The hard truth is that when documentation breaks down, it causes bugs. The most recent Wilson Research Group and Siemens EDA functional verification study found that the second and third leading causes of functional flaws in respondents' ASICs are changes in specifications and incorrect or incomplete specifications, accounting for about 50% of bugs. That's significant. If you can improve documentation processes, you can reduce costly bugs, and that's what we're all here for. It turns out this documentation problem isn't unique to silicon projects. It exists in software projects as well. Over the years, developers have devised agile processes that help them improve programmer productivity and code quality. A core value is effective collaboration. To that end, they came up with Behavior-Driven Development, or BDD. Many agile techniques focus on manageable incremental changes to code, covering one new feature at a time. The objective of BDD is for colleagues to collaborate and communicate from the initial idea through to the delivery of a working increment, guided by a shared understanding of what the code should do, its behavior. BDD consists of a series of activities with 4 types of actors. The business people represent the end user and have insight into what behaviors will provide the most value. Their role here is non-technical in that they aren't hands-on with the code. The developers will code and deliver the working increment, and the testers will test it. Having these 3 amigos collaborate from the very beginning is a shift left that helps identify problem areas sooner and prevent some defects from getting introduced in the first place. The last actor is the computer, because running code is part of the process. To kick things off, business, developers, and testers all meet in a series of discovery workshops, short, focused meetings in which they define the intended behavior and, most importantly, come up with concrete illustrative examples. They write all this down as informal notes such as handwritten index cards. Next, a subset of the group convenes and formulates their informal notes and examples, or scenarios, in a text format that's written in a natural language so it's human readable, but has enough structure to also be machine readable. This is executable specification. At this point, the developer takes that spec and implements the increment. Meanwhile, the tester takes advantage of that same spec's machine-readable structure to prepare an automated test environment. When everything is ready, the developer and tester execute the executable specification on a computer, running the automated tests against the code until they pass. When they do, the increment is done, and they can include the tests in their continuous integration regression suite to guard against changes that could break things. The executable spec becomes the test. This is known as living documentation. Let's go through a simple example. Pretend you're on a team that's developing an arithmetic logic unit. You're in the division that does division. Sales have been great, but now you need a new integer division function because your users are so over fractions. You assemble your three amigos for a discovery workshop. You grab a marker and write down the name of the feature, ALU division, on a yellow index card and put it at the head of the table. Next, you summarize the behavior on a blue index card and put it under the yellow one. In integer division, the remainder is discarded. Now it's time to come up with a series of concrete examples using actual numbers. So, here's where you come in. If there's someone in the room with you, turn to your neighbor and together concoct some examples of integer division with actual numbers and what the expected result should be. If you're alone, just talk to yourself out loud. Try to think of some key corner cases and exceptions, examples that could get you to 100% code coverage. Take turns and come up with one or two each. If you're taking notes, jot down your examples. Take 60 seconds to do this now. And go. Here are a couple examples I came up with. We write down our examples on green index cards and put them under the blue one. 15 divided by 4 should be 3 because you throw away the remainder. Here's an important case. 10 divided by 0 should result in an error notification. If any questions came up, like how do you handle negative numbers, you write those on red cards and chase down the answers later. At the end, you'll have a tree of index cards that captures the behavior in layers that add detail as you go from general to specific. But you can't execute index cards, at least not without punching little holes in them. You need to organize these notes into an executable specification, and for that you need a file format that has a little machine-readable structure to it that doesn't get in the way of humans reading it. The solution is Gherkin. Gherkin is the name of a domain-specific language purpose-built for writing natural language specifications. It was introduced with a popular BDD tool called Cucumber, so the name is in keeping with the theme. Gherkin is open source and has become a de facto standard. After the discovery workshop, a couple of you get together and write a Gherkin file that captures all the notes from the index cards. You might come up with something like this, which is a small, complete example of a Gherkin feature file. It's a plain text file, so you can use your favorite editor to create it. Many modern editors have plugins for Gherkin that give you syntax highlighting, auto-completion, and formatting. Comments start with the #. This one reminds us that Gherkin file names should all end with .feature. The next line uses the feature keyword to give a title for your feature. This is your blue index card. This block is free-form multi-line text purely for documentation purposes. This feature is illustrated by 2 concrete scenarios corresponding to our 2 green index cards. Each scenario is composed of steps beginning with the keywords given, when, or then. Steps are the real body of the feature file, and the given, when, then pattern is its soul. Given steps are for setup or preconditions, here declaring the initial values of our operands. When steps are the triggering actions, in this case performing the division. Then steps are basically assertions for the expected outcome that make this executable specification self-checking. If a then assertion fails, then the test fails. It's traditional in BDD to use the verb should here, but you can use stronger verbs like shall or must if you prefer. So in general, given some initial state, when somebody takes some action, then this subsequent condition should be true. This last keyword, and, is syntactic sugar. It makes the scenario more grammatical and readable than repeating the previous keyword, then. Here's a second scenario for your divide by zero case. Notice that some steps are the same or very similar with just the values changing. So steps can be parameterized and reused. The Gherkin language is defined by the leading keywords, and they provide the structure for automation tools. The rest of the text is for humans. Now it's your turn again. I want you to turn back to your partner and out loud rephrase one or two of your examples from before using the given, when, then pattern. Take 30 seconds. Go. These are the basics of Gherkin. There's more to it, so I encourage you to type BDD Gherkin into your favorite search engine to learn the rest. You'll pick it up in less than an hour. Our discussion up until now has been generic and could apply to any programming language. BDD was invented for software projects, but I contend we can use it for silicon projects too. RTL and verification environments are code, and front-end ASIC and FPGA development have much in common with pure software programming. The roles and actors are largely the same. You have project owners or technical management representing business, you have RTL designers as developers, and you have verification engineers starring as testers. Now, it's true that ASIC projects have different life cycles and timelines than Agile software projects, so BDD scopes and schedules need to be adapted accordingly. Large SoC projects are different from FPGA projects, which are different from pure IP projects, but their deliverables can all be divided into manageable increments. You can also use BDD to define and validate verification components themselves, not just RTL. For example, reference models or protocol checkers. In that case, the DV folks are the developers, probably the testers too. This is all great, but the problem is BDD tools don't support SystemVerilog, at least not until now. This paper introduces Bathtub, which is a library I wrote entirely in SystemVerilog that enables BDD for silicon projects. The name is a backronym for BDD Automated Tests Helping Teams Understand Behavior. Bathtub begins and ends with behavior. It's built in UVM, so it integrates seamlessly with your existing test benches. You run it in your simulator along with your device under test. It reads and parses your Gherkin feature files and executes them as tests. Under the hood, Bathtub is an engine that runs UVM virtual sequences on your environment's existing virtual sequencer. A couple years ago, I was researching possible solutions to some of the documentation problems we discussed earlier. I discovered living documentation and BDD and was intrigued and also a little jealous because we SystemVerilog enthusiasts were left out. So I ported Gherkin to SystemVerilog at my previous employer, Everactive, and got it working on a limited experimental basis on our current project at that time. I don't work there anymore, but before I left, they were gracious enough to release Bathtub as open source software so it would still be available to me, literally so that I could present it to you all here today at DVCon. So I'm not a long-time BDD expert. I'm an enthusiastic newbie. Right now, Bathtub is a really fun personal project I tinker with in my free time. Back to our BDD flow. You held a discovery workshop and generated index cards. Then you formulated the scenarios in a Gherkin feature file. That was all generic, the abstract base class, if you will. So, how do you extend it into a concrete silicon project using Bathtub? Your RTL designer takes the specification and goes off and implements the RTL. Meanwhile, you, the DV engineer, take that same specification and write some glue code using Bathtub utilities so you can run the file as an automated test. You need to write tasks and assertions that implement each of your given, when, then steps. SystemVerilog doesn't understand your natural language, at least not yet, but who knows what generative artificial intelligence will bring. Until then, you need to translate English to SystemVerilog yourself. You will encapsulate your tasks and assertions in individual UVM sequence classes. In BDD, these classes are called step definitions, and they'll take parameters so they can be reused. The other piece you need to write is a new Bathtub test. It's just like the UVM tests you already write, but you won't run a default sequence. You'll instantiate and run a Bathtub object instead. Now you're ready to execute your specification. Launch your simulator, compile the RTL, your UVM test, and the Bathtub package. Actually, just like in test-driven development, or TDD, you're supposed to run everything first without the RTL changes so you can see your test fail without it. Then you and the designer work together, guided by the failing tests, to add the new RTL code until everything passes. At that point, the feature has met your acceptance criteria and can be declared done. This is an example of a complete step definition, the UVM virtual sequence that translates your English given, when, or then step to SystemVerilog code. Your ALU feature file has 4 different steps, so you'll need to write 4 respective step definitions. The first step is given operand A is 15 and operand B is 4. You declare the class and give it a sensible name, set operand A and B vSequence. This class extends a base class, ALU base vSequence. The assumption here is that you follow UVM best practices, so you already have some kind of test bench with an environment and a virtual sequencer, and you already have virtual sequences that run on it. You likely have a base class for your sequences that takes care of common setup steps and that probably provides some convenient methods you can use in your concrete child classes. That's what ALU base vSequence is. Your step definition extends that same base class as is, so it can do the same things your other virtual sequences can do. Lastly, your step definition needs to implement the step definition interface class from the Bathtub package. This line uses a Bathtub macro, backtick given, to declare which English phrase will map to this step definition. There are also backtick when and then macros. Notice that the string uses the %d format specifier for integers. That's how we parameterize this step definition to take any integers, for example 10 and 0. Bathtub recognizes all the SystemVerilog format specifiers. Speaking of parameters, here you declare 2 integers, operand A and operand B, to hold your 2 arguments. This is the usual stuff you need for UVM objects, the object utils macro and a constructor. You override the sequence body task to do the work of this step. First, you use some Bathtub macros to extract the operand arguments from the step string. You make a sandwich of step parameter get args begin and step parameter get args end. Inside, you call the step parameter get next arg macros twice, once for each argument. Each call gets the next integer from your string and stores it in your variable. The macro argument int should match the type of the variable declaration so the value is converted correctly. After this, operand A should be 15 and operand B should be 4. Finally, the body does the work. You simply call the convenience methods set operand A and B supplied by your base class. And that's it. Presumably, the convenience methods start some subsequences or transaction items with UVM do macros or equivalent. Recall that to automate the tests, we also need to write a bathtub test. Here's what the complete Bathtub UVM test bench will look like. The shaded regions are specific to Bathtub. Everything else can be reused from your normal test bench unchanged. The step definitions you created store themselves in the UVM resource database, thanks to those given, when, and then macros. This shaded block is your new UVM test. I call mine bathtub_test. It instantiates your UVM environment just like all your other tests. That environment has agents with sequencers and drivers that connect to the DUT with virtual interfaces, and it has a virtual sequencer that controls all the subsequencers. Your test must also instantiate a bathtub object from the bathtub package and configure it with the file names of the Gherkin feature files and a handle to your virtual sequencer. In the run phase, your test calls bathtub method runTest. RunTest reads your feature files, parses them, and builds a list of steps. It processes the steps in order, retrieves their step definitions from the resource database, instantiates and provisions the step sequences, and runs them one at a time on your virtual sequencer, then exits. This is my favorite part. This is how Bathtub automatically stores and retrieves step definitions in the UVM resource database. This blue table represents the resource DB. At the start of the simulation, it's empty. Recall that the resource DB stores an item with 3 keys, the item's type, a scope, and a name. You're storing sequences, which are UVM objects, so the type is UVM object wrapper. Normally, the scope column holds a hierarchical component path, which takes wildcards, so the scope is internally stored as a regular expression. The macro takes your step definition template string, converts the format characters into regular expressions, and stores that converted string as the scope. Bathtub stores a constant string in the name column, so the rows are distinguished solely by the regular expression. Finally, the value column holds the object wrapper for the sequence as returned by getType. Those hard-working given, when, and then macros in your step definitions take care of all of this for you. At time 0, the macros call UVM resource DB set to store their object wrappers in the resource DB indexed by regular expression. Here you see all 4 entries for our ALU example. When you run your test, Bathtub compiles a list of step strings from your feature file. Here's the first one with operands 15 and 4. Bathtub calls UVM resource DB get to search the resource DB for a regular expression that matches this string. Lo and behold, there's a match. This regular expression would match any 2 integers, for example, 10 and 0. You've heard of a content addressable memory, or CAM. Well, we're using the resource database as a content regular expression addressable memory. Bathtub takes the matching object wrapper, instantiates a sequence from it, and configures the sequence with an actual string with the 15 and the 4 in it. That's how the step parameter getArg macros in your step definition are able to extract the parameters when the sequence runs on your virtual sequencer. As I said earlier, I wrote Bathtub at my previous job and deployed it on the system on chip we were developing. We conducted a small discovery workshop with the manager, the RTL designer, and myself on DV. We used a collaborative whiteboard app to capture our colored index cards virtually. I wrote the Gherkin feature files and the step definitions myself. We got all of the tests to pass and included them in our regression suite. Functionally, it was a complete success. I learned a few things. BDD is not verification. It's awesome for directed testing, but you still need traditional testing to find bugs and close coverage. That being said, if you get the BDD tests to run first, they smooth the way for further verification to follow. I was surprised how difficult it is to write good feature files. The internet is full of passionate articles about the do's and don'ts of Gherkin. It's an art to find the right level of detail and to strike a balance between readability and ease of implementation. Once we had executable specifications, they were useful for actively developing and testing new features and as reference material after, but they couldn't replace all our legacy documentation, and we continued to write new documents the traditional way. Project managers might enjoy the clarity a feature file brings to planning and progress reporting. If a file has 10 scenarios, those are 10 well-defined tasks which are easily tracked. Gherkin files are decoupled from the design and are easy to reuse. I used our RTL feature files unchanged to verify my own reference models. The given when then pattern is a powerful archetype. It's like a mini 3-act structure for code. I found myself using it mentally in SystemVerilog assertions, functional coverage, bug reports, and even tech support tickets. Writing step definitions is fun, but I had to write dozens of them, and it was time-consuming. I found myself rewriting, refactoring, and reorganizing them a lot. BDD is great, but it's an open question whether the time spent provides adequate return on investment. My favorite benefit is how much Bathtub helps debug. It prints every line from the feature file to the simulator log file as it runs, so the test is self-documenting. And since the feature file is read at runtime, I could modify it and rerun it without having to recompile. Lastly, this experience demonstrates that SystemVerilog is a capable language that can handle general-purpose computing applications beyond the simulation of circuits. Bathtub is available today, open source, at this URL. Given a silicon project that is on the bubble, when you turn on the Bathtub flow and you get it running, then you should scrub through your features to deliver clean code, and away go troubles down the drain. Thank you very much for your time.